All right. Hello, everybody. We are doing, let's see, 2.2 today. 2.2, the second um, lesson in our derivative unit. Okay, one of my favorite units. And yesterday we talked about exactly what a derivative was. Okay, we talked about kind of the formula behind it and what it means when we're finding the derivative, all that good stuff. Okay, so we're going to do a little practice for that for warm-up. So use the definition of a derivative to find the derivative of. You can do it for 1 and for 2 here. You can do it either way. I mean, you could use either formula. Like, for instance, okay, maybe for this one I would use the, just to give yourself a little bit of practice, maybe try doing the limit h approaches 0, f of x plus h minus f of x over h. Maybe do that one for number 1. And then for number 2, maybe try doing the other definition of a derivative. So this is the average rate of change one. Again, I mean, it doesn't really matter, but see what you can do there. And we'll discuss the warm-up and what it means in class. Okay. All right, so let's talk about what we're doing today. Again, we know what a derivative is now. We're going to discuss the derivative as a function. Okay, so when we learned the derivative, we mostly learned it as like this is how you find the derivative at a point. We learned about how we find the slope at any point on a curve, right? If I want to know the derivative of x equals 1, we know how to do that. Okay, well, the good thing is we can find like the derivative as a function of something. So what that means is this going to be a function that tells us the slope of the tangent line of f of x at every x value. So it's just another equation that you could use. So we're finding an equation that describes the slope of all the tangent lines at any x I want. Okay? It's going to be pretty cool. And here's the notation. Here's the notation that we use. So like if my function was y, then the derivative would be what we say y prime. That's the notation that we'd use. Or if we decided to say f of x as our function, then this is how we would write the derivative. We would say f prime of x. And here's a bunch of other ways to write it. We use this one a lot, dy over dx. That's how you read it, dy over dx. Again, that's just another way of saying the derivative at some point. It literally means that you have a change in y over a change in x, which is what a slope is. So maybe start these 3. Don't really use many of these other ones that often. Maybe sometimes this one. This means actually, how this is read is you're going to take the derivative of your original equation. So sometimes I'll write it that way, but mostly these first 3. Okay. All right. Well, let's kind of have a discussion about the derivative as a function. And I like using x squared as my little intro to that. It says find and graph. All right, f prime if our original function is x squared. Okay, our original function is x squared. So let's first start off by actually finding what f prime is equal to. Okay. Now remember from yesterday, f prime of x is going to be equal to the limit. And I always like to use that second definition of the derivative. I think it's the one that we need to use when we're not given a specific point, right? As h is approaching 0 of x plus h squared minus f of x. Oops. I meant to write the definition first. So f of x plus h all over h. Okay? Now, let's just quickly solve this because we mostly learned this yesterday. But this is equal to the limit. H approaches 0. F of x plus h is when we plug x plus h into my f of x equation. So that's going to be, instead of x squared, it's going to be x plus h squared. And then minus f of x, that's just the same thing as x squared. So minus x squared over h. And once we set up the definition, it just goes back to our limits unit, just being able to simplify and reduce our limits unit. So that's nothing new. Let's just do that real quick. H approaches 0. I'll expand the top. And you'll notice that some nice things happen whenever we take the derivative using that formula. The negative x squared and the x squared cancels. So I'm left with the limit h approaches 0 of 2xh plus h squared all over h. And you'll see that an h, an h, and an h cancels out. And I'm left with the limit as h approaches 0 of 2x plus h over 1. And if I plug 0 into that, I get 2x. Okay? So we found the derivative, and that means that f prime of x is equal to 2x. That's a very interesting thing there. F prime of x is equal to 2x. That means that the derivative at any point on my original graph is just going to be 2 times x. So let's discuss what that means. Okay? Let's think about this graphically. All right? So here, I'll kind of draw a little dividing line here. We just said that, okay, so we got f of x is equal to x squared, right? And we just showed the math that f prime of x is equal to 2x. So we know this to be true. Let's discuss how this graph is going to look, okay? So let's start by graphing f of x. F of x is a parabola, okay? You know what a parabola shape looks like. There it is, okay? Now, if I were to graph f prime of x, okay? F prime of x is the line 2x. So it's just a simple line. We're going over 1 up 2, and the line looks like this. Okay. Now I want us to make an observation here, make some comparisons here between f of x and f prime of x. Now, f prime of x, remember what a derivative function tells us? It tells us the value of the slope at any point on the original graph. So let's make some observations here. What is the slope of the tangent line at the origin? Well, you can see that it's a minimum here. It's changing directions, and we know that that slope is going to, you can see the tangent line is equal to 0. All right? So f prime of x here equals 0. What's the value over here on my graph? It's 0. That tells me that the slope, all right, the tangent line of the original graph is 0. And we can see that that value is plotted here. Well, let's again think about it. All right, the slope right here, the slope right here. Do you see how the slope of the parabola is getting more and more steep? All right, so f prime of x is going to be positive and getting bigger. Do we see that? Do we see that the slope of this parabola is getting steeper and steeper? So that means that the slope value is going to be getting larger and larger. Think about it. Let's say that this slope is 1, this slope is like 3, this slope is 9. I mean, do you see how the slope is getting steeper and steeper and steeper? Well, look on my derivative graph. This value is 1, this value is 3, this value is 9. The outputs of my derivative, the outputs, I'll write that. The output of f prime of x, all right, is the slopes of f of x. I mean, you can see the same thing over here. Like, it's getting steeper and steeper in the negative direction. Okay, so as I go to the left, I'm getting higher and higher negative numbers. So you can see, like, it's doing the same thing over here. So all a derivative is the outputs, okay, of whatever my slope is in the original graph. And we can find that relationship. So let's say that I wanted to know the derivative at, what's f prime of 1? Okay, well, that's going to be 2 times 1, which is equal to 2. And we can even see right here at 1 that that slope looks like a slope of 2. So that's kind of a cool observation to make between the derivative as a function of the original function, of the original graph, original function. So we'll see the graphs looking very similar, and we'll learn how to graph based off of the original function too. So yeah. So here's another great example of a graph. We're given f of x, in this case f of t, whatever, and we're asked to draw the derivative of that graph. Okay, so it says the graph of f is given. We're going to draw f prime of x. This is another great way to make a relationship between the original graph and its derivative function. Okay, now let me give you my tips on how I graph based off of the original function. And it's all really just an estimate since we're not given the original actual equation. So just make a little note here that we're estimating. So we're going to estimate the slope, okay, of the tangent line to sketch f prime of x at, and we'll have multiple x values. All right. So we're going to try to keep the same scale here. So let's draw. So this is going to be f prime of x. You could draw it on the same graph above if you really want to. I'm going to just kind of sketch it below. I'm going to keep them separate so you can kind of see what we're dealing with. All right, looks like we're going 20, 40, negative 20, negative 40, and we're doing, looks like 2, 4, negative 2, and negative 4. All right. So remember that the outputs of f prime of x are just the values of my slope in the original equation. So where I start is where I think the obvious slopes are, and that's like at my maxes and my mins. If you were to draw a horizontal tangent line here at these points, what does that tell me? I think it's pretty clear to see that the slope is equal to 0. So if I were to do, so right here at negative 2, the slope is 0. So that means that f prime of x, his output, is 0. So I'm going to plot 0 and negative 2, f prime of negative 2. And I should write that right here instead of f prime of x. So this will be f prime of negative 2. Apologize. So the output here is 0. Now, same thing over here at positive 2. So it looks like the slope is 0, so that means that f prime of positive 2 is also equal to 0. So I'm going to plot that point here. Okay? Now, I'm going to sketch it kind of from this point as well. So we know those are pretty much a guarantee. Okay? Now, the rest are just going to be kind of an estimate here. And let me show you what I mean. Like I'm gonna choose maybe, since negative 4 is right here, I'm gonna choose maybe 0 here, and I'm gonna choose maybe positive 4 as my other points. I'm just gonna estimate them and plot those values. Okay? Now, if I were to plot a tangent line here, okay, I'm gonna do it kind of like right there's my approximate tangent line at negative 4. Okay. Now we're going to approximate that slope real fast. I'm just going to do it like old-fashioned way. I'm going to do kind of rise over run here. It looks like that we're doing, y'all can help me out with this. I'm going to kind of do a little dotted line down. There's my rise, there's my run. It looks like I'm going from maybe, I should probably pick a better triangle than that. Maybe I'll do something like this. I'll go like down and maybe like over this way. It looks like my run is like -4 to -3. It looks like I'm going positive over 1. And then if you kind of match it up here, it looks like my rise is going from -20 to +20. So that's a difference of 40. Okay, so in a way, this kind of looks like that f prime of -4 is going to be 40 over 1 or 40. That's what the slope kind of looks like to me for -4. And again, I just estimated it. I just drew a tangent line and tried to estimate the rise over the run. It kind of looked like we were going between -20 and 20, and we were going over 1. So that's just a really quick approximate. So I'm approximating that f prime of -4 is 40, so I'm going to plot that point right here. That's the value. Okay. And it looks like as I'm getting closer and closer to -2, my slope is becoming less and less steep. So the values are getting lower and lower in the positive direction. So it looks like I'm kind of doing this right here. Okay. Now, so that's what I'm saying. Like anytime between -4 and -2, I have positive slopes. But once I go past -2, I start to have negative slopes. So let's estimate this negative slope right here at, I'm going to try my best to draw a really good tangent line here at 0. So we're estimating f prime of 0. All right, so what's the best? I mean, if I were to keep doing this line down here, I'm trying really hard to draw a good tangent line. It looks like I'm going kind of from here to here, so I can go like down, rise, over, run, something like that. That's a terrible drawing. I apologize. But it kind of looks like I'm going from maybe 20 over 20 to -20, so that's a difference of 40 again. But it looks like I'm going over from -1 over to 2, so maybe a difference of 3. So, I mean, maybe like 40 over 3 or something in the negative direction. I mean, that's a terrible, that's like what, 12 point something. So we'll say like, we'll just approximate -12. Okay. I mean, that was just a very rough approximation. So just trying to do the slope of this line here. But I'm going to plot that point like right here. Okay. And as you can see, it's all negative values, but as I get closer and closer to 2, those negative values become smaller. So it looks like I'm kind of doing this shape right here. Okay. And now those negative values are getting smaller and smaller. I'm just connecting the dots here. And then when I get to +4, it looks like I got a really steep slope again. Kind of going all the way from 40 down to, let's see, I'm trying to draw the best triangle that I can here with points I can see. But it looks pretty similar to before. It kind of looks like, I'm just going to guess it's the same slope as this other value at -4. I'm going to guess again that's at 40. All right, so I'm going to say f prime of 4 will equal 40. And again, that's just a rough approximation. I'm going to say kind of like that. Now, I mean, if I'm asked to estimate what the graph looks like, okay, you're just testing out slopes. All right, you're testing out slopes and just estimating. And don't stress that it's not exactly 40 or something like that. That's kind of the shape I was wanting you to kind of get to. So, not bad. All right, not bad at all. So remember that the outputs of this graph are just the values of the slope above. So like if I said, hey, what's the slope at 3? You can say, oh, well, that's approximately 20. You go over to 3, it looks like it's approximately a slope of 20. Yeah, something like that. That's kind of how it works. But I'm going to practice this a bunch, guys, so don't stress. All right, I got a couple more slides I'm going to try to squeeze in, and as usual, we'll finish off the notes in class. But it says right here, how can a function fail to be differentiable? All right, how can it fail? How can a function fail to be differentiable? Well, let's go back to the definition. Let's think about it. We'll look at the graph first, though. It says that the graph of a function changes directions abruptly. Now, the best example we teach is like y equals the absolute value of x. You know how it does that little V shape? You know how it abruptly changes direction? This causes the graph to have like a kink in it or a corner. Again, you can see that right here in the absolute value. Then the graph of the function does not have a tangent line at this point. You can't draw a tangent line at this little V right here. Okay? And f is therefore not differentiable there. Okay, so whenever you actually try to do the definition of a derivative, actually compute the function, you'll see in trying to compute the derivative, you will find that the left and right limits aren't the same. They're different. Okay? So that's one way that it's not differentiable. If f is not continuous at a, then f is not differentiable at a. So again, if there's like some jump discontinuity or something, then they're not continuous at the same point. And if the curve has a vertical tangent line, okay, then there is no, it's not differentiable there. So here's graphically what I'm talking about here. Here's a vertical tangent line at a cusp. Okay, it's almost like having like a asymptote there, if you want to think of it that way. So you see that like right here it may be continuous, but there is like a sharp change in direction. So it's not differentiable at x equals a. Okay. Here is like, okay, so here's a change in concavity right here. So we're kind of like going concave down to concave up. So this is actually called a point of inflection. Now, this isn't an abrupt change in direction, so not always, but sometimes, not differentiable. But it's more so going to look like this to the left. That's more so what our graph's going to look like. If we have a continuous function, then this is what it's going to look like when it's not differentiable. Okay. Now, by definition, a function is differentiable at a point A if f prime of A exists. So like, if I can do the definition, all right, plug in A and I get an actual limit, if I get an answer, then that means that the derivative exists. That's algebraically how you show it. It is differentiable on an open interval A to B, or A to infinity, negative A to A, or all values, if it is differentiable at every number in the interval. So that's how you talk about it being differentiable in an interval, is if you can do f prime of any point on that interval, it's differentiable in the interval. Okay? So the best example we do to teach is, where is the function f of x equals the absolute value of x differentiable? Okay? So let's think about this. We've discussed this in a previous lesson. We know what the parent function of absolute value of x looks like. It's like that. Remember how I told you by definition that an absolute value is actually just a piecewise function? Remember how I said that this is the same thing as negative x whenever x is less than 0, and x whenever x is greater than or equal to 0. So here is that y equals negative x. Here is the y equals x portion of it. Okay, and you can see that right here at this point here, this corner, we have an abrupt change in direction. So we have this like little cusp looking thing. So at this point, it is non-differentiable. Okay. But everywhere else it is differentiable. Everywhere else, I mean, think about it. Okay, and we're going to really go over this later. But it's differentiable at every single point leading up to the cusp and every single point going past the cusp. So it says, where is the function differentiable? It's differentiable from negative infinity to infinity, except at x equals 0. Okay. And again, we're going to go over this later, but this is what the derivative function looks like. Okay? If I were to graph the slopes, or the derivative function, think about it. All we got is two lines here. To the left of 0, what's the slope always going to be? It's a line. It's the rise over run here. The slope is always going to equal -1. So any point I look at to the left, all right, of 0, the slope is always going to be -1, no matter what, except at 0. And then anytime I go past 0, the slope is always going to equal +1. So here at 1, the slopes, anything to the right, that value is always going to be equal to 1 except at 0. So that's what the derivative function looks like. And you can see that the left and right limits do not match up. So therefore, the values exist in the derivative everywhere but at 0. So that's a pretty good observation, and we're going to graph that a lot more later. All right. So it's because of this idea that we got this theorem. This is very important when we're doing late theorems later on down the road. This is going to be a great explanation for us. So I would really highlight this bottom part here. Okay. That if f is differentiable at a, f is also continuous at a. Right? So what that means is that if I have a differentiable function, then I know that every point on that interval is also continuous. But you got to be careful because the converse is not always true. Okay? There are functions that are continuous but not differentiable. For instance, the one we just looked at. This function is continuous for every single value of x, but it's not differentiable for every single value of x. We saw that at 0, we had like a cusp. We had a sharp turn. Okay. So that's a pretty good example there. Let's see how much time I got left. 27 minutes. So, okay, I'll just write a couple more things here, and then we'll leave off this slide. So just a reminder that if given that f of x is differentiable, we know f of x is also continuous. Okay. But again, just because a function is continuous or continuous doesn't mean that it's necessarily differentiable, right? But this is going to be a reason we use later on down the road. All right, let's see. I'm at 28 minutes. That's not enough time for us to go into this last example here. So we're going to save this for notes in class. But as usual, thank you so much for your patience and for watching. Nothing more than 30 minutes of a video at night. That's not too terrible. So we'll go over these last couple slides later. All right, good job, guys. As always, y'all are awesome, fantastic, good people. All right, bye-bye.